Welcome back to a new video about current sources using transistors. We continue in this example using the MOSFET. In this example number 1, we will look at the simple current mirror using two MOSFETs. And of course, we will work out the calculations for this and also verify this in SPICE simulations. So let's look at our circuit. As said before, we have two transistors, M1 and M2. They are the MOSFETs called the N-channel enhancement MOSFET or E-channel MOSFET. The parameters for both of the transistors are the threshold voltage of 2 volts, conduction parameter Kn is here 25 milliamps per square volts, and there is no channel length modulation. So that means lambda is 0. Now we would like to design a load current of 1 milliamp, which is shown here. This is the ID2, drain current of M2, and we have a VDD of 10 volts here, and M1 is equal to M2. That means they are matched. That means they have the exact same parameters like is shown here, but also in physical dimensions like the width and the length and all those parameters. They are exactly the same. So they are just an exact copy of each other. In this case, that means we have seen also in the BJT variations that the ID2 here was approximately IRF, but since the gate current here in the MOSFETs, which is actually the base current of the BJT, that is very close to 0. It is approximately maybe in the femtoamps, maybe in the nanoamps, depending on the technology. So that means the ID2 is very close to IRF, so we can almost say it is equal to IRF. So let's see how we can work this out. So the solutions, now let's designate again here, before we move on to calculations, the nodes here, X and Y. Maybe we don't need that, but it's always handy to designate them. So before we move on, let's also look at the voltages. The VGS1 here, which is the gate to source voltage of M1, is exact same as the VGS2, which is from M2. That means they are exact same gate to source voltages. That has an effect on the drain current. We will see that shortly in the formula. Now, when we call this just this VGS, which is also VGS1 and VGS2, we just define now the VGS here. Now the Kirchhoff voltage law, for looking from the top to the ground node, we can say it is VDD plus the voltage across the R. It is R times RF using Ohm's law, and then plus the VGS1 or VGS2, but just of course VGS. Now we assume that the transistors operating in the saturation region, that means these two conditions we need to satisfy, so we will check that shortly. But we just assume that it is correct, so we will check afterwards. Now the drain current ID2 is given here, is given by this expression. You can see the conduction parameter and also the threshold voltage, and since it is VGS1, we can also call it VGS, it's the quantity squared, and we have now our current. This is without the channel length modulation. Now we can now divide now the Kn left and right hand side, you can see here, and then when you solve this in the generic form, you have the square of the left side, of course a plus and a minus variations, that will give you this, and you equate now the VGS in terms of the other parameters, you get this. What you see is there are two solutions. One of them is the plus of the square root plus the V threshold, the other one with the minus sign. Now we can now work it out by substituting the values we require for the drain current and also for the Kn, etc. Now you get now these two values, which is VGS is 2.2 volts or VGS is 1.8 volts. Which one is now valid? Now this is larger than the threshold voltage. That means it is valid because of the saturation region conditions. So this is valid, but this is less than the 2 volts of the threshold, so this is not fulfilling the first condition, so it is not valid, so it's invalid. Is this first condition now valid? That's definitely valid, because that is the drain to source voltage, which is also the gate to source voltage, which is exact same, but we need to have a drain to source voltage which is larger or equal to the VGS minus the threshold. That means it is then 2.2 minus the threshold, which is 2, it must be then 0.2. Well, that is definitely the case, so we also fulfill that. Now, that means in this case the VGS, what we need is 2.2 volts. We will use this, and our assumption of the saturation region is also correct. Now, we know that the IRF here, in this form, looking at node X, is actually equal to ID1 only. Why? Because the gate of 1 and gate of 2 is 0. It's not like in the BJT, this is actually more simple. So that is also equal to I2 VGS2. Why? Because ID1 is equal to ID2 because of the VGS1 and VGS2 is equal, and the dimensions are exact same because we said already M1 is equal to M2, so they are matched. This is only valid if you have that condition. Then we can write the following using the Kirchhoff voltage law here. Rewrite it: R is equal to VDD minus the gate to source voltage over the IRF or ID2. We know VGS, which is 2.2. We know IRF, which is ID2, which is 1 milliamp. Now, when you calculate now this, you get now 7.8 kilo ohm or 7,800 ohms. That's now what we require. Now, in general, we can say now the following. That is important to know, that the load current here, the ID2, divided by the reference current here is related by this expression. Now, in general, you see also the lambda, which is the channel length modulation. Now, the Kn2, which is the conduction parameter, is written out like the mu n Cox and W over L, which is this parameter. You see here the dimensions, the physical dimensions, but you see the following. This is for both transistors exact same, so we can divide it out. Since we have the same threshold voltage, so V threshold 1 and V threshold 2 are exact same, and also the gate source voltage are exact same, we can also divide these two out. We also know that the lambda is equal to 0, so this is 0 and that's also 0. So what you left here is only the dimension ratios, because this is a 1, this is 1, so you only have this expression. Now, this is a very simple and nice expression because it is just the ratio of the W over L of the second transistor and the W over L of the first transistor. So if you make this W over L ratio, let's say 10 times larger than this one, you'll get 10 times more current here. That's basically the idea. Okay, let's bring this together and now check also our result in the simulations. This is what we have, so VGS2 and also the 7.8 kilo ohms for our resistor. Now, this is the circuit. You see here the IRF, which is 1 milliamp, and also the ID2, which is 1 milliamp, so that is also what we have said here. You also see that the ID1 is 1 milliamp. You can see the I gate 1 and I gate 2, I just put it here purposely. It is 2.2 approximately femtoamps, and femto is 10 to the power minus 15, so you can almost say forget about it. I also put here the dimensions. You can see the length and the width, so this is 100 micrometers. Quite large, of course, looking at the modern technology, but that's just an example. But they're exact same. Since they're exact same, the copy is also 1 to 1. So that is also what we see here, and it is according to calculations. So this resistor with this voltage and this configuration of the MOSFETs will give us the required load current. Now, looking at another analysis, which is the load voltage versus load current. Now, that circuit is now changed like this, so you can now split this node here and put this to 10 volts. But now you have to sweep this VL value, so you change the value of this DC voltage source, and you look at the value of this ID2, which is our load current. Again, the same MOSFETs, everything is the same, only this change. What happens? This is the plot. The vertical lines are the load current, ID2, and this is the load voltage. I changed it from 1 to 19 volts. You can see it starts at 1 milliamps and it increases very slowly and slightly. You can say how much increases that. Now, looking at the first here is 1.000002. So you can say there's almost no change here. That's the basic idea actually of a current source, because you don't want to have a huge change when this potential in your actual circuit is changing. We will see that later in other videos, that we will put this node directly, for example, to a differential pair to give the required tail current or for an amplifier. Now, you don't want to have a different current because that potential is changing. You just want to supply the constant current. That's actually the idea of this transistor configuration for the current source. Alright, this is our example number 1 about the MOSFET current mirror using simple 2 transistors. We have seen that the calculations really match our simulations, and we also have discussed the load voltage versus load current. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.